Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Assalamu alaikum, dear students. Today in our lecture number 8 we are going to study the part 1 of the soil compaction. Soil compaction is a very important topic and lecture in geotechnical engineering 1. First we will start with the introduction of soil compaction. Then we will move towards the principle of soil compaction. We will also discuss in our today's lecture the difference between compaction and consolidation. Fundamentals of compaction will be discussed. Compaction curve, which is obtained in lab, will also be briefly discussed in our part 1 lecture, but that compaction curve is discussed in greater detail in our part 2 of the lecture. Factors affecting the compaction, for example, how the compaction will change if we are varying the water content, or if the degree of saturation is varying, if we are changing or using different types of soil, whether it's gonna affect the compaction characteristics of that particular soil, amount of compaction effort. If we are increasing the compaction effort, how the compaction will change, or the unit weight will change, or the density of that particular soil will change. And we will also discuss in our today's lecture the method of compaction, or the effect of method of compaction on the density or the unit weight of the soil. Now, in the construction of highway embankments, earth dams, retaining walls, slope stability problems, loose soils must be compacted to increase their unit weights. To compact a soil, that is to place it in a dense state, the dense state is achieved through the reduction of the air voids in the soil with a little or no reduction in the water content. So in compaction we are removing or reducing the air voids in the soil. Now hence the soil compaction is the densification of a soil through the expulsion of air, which requires mechanical energy. If we are talking about the mechanical energy in lab, various rammers are used. When we are talking about the mechanical energy in the field, so various types of rollers or handheld plates and rammers are used. This process must not be confused with the consolidation, in which water is squeezed out under the action of a continuous static load. Consolidation is an in-depth topic which will be discussed in geotechnical engineering 2. So here you can see a roller is being passed on the soil. So first we place it in a loose state, and then we sprinkle some water on it, and then we allow this roller to pass on it to compact this to the desired density. Now compaction increases the unit weight of soil and decreases the void ratio, which further enhances the strength characteristics of soil, which ultimately gives us the higher bearing capacity of that particular soil. Compaction also decreases the amount of undesirable settlement of the structures and increases the slope stability of the embankments. For example, if you are having a loose soil here, and if you use rammers or in the field we use rollers, then it will come up to a much more denser configuration, and you can clearly see that lots of solid particles will be present in the compacted or denser configuration, and this will eventually increase the weight per unit volume, and the unit weight will increase in the compacted soil. I have written the overall objective of the compaction here, that the overall objective of the compaction is the improvement of engineering properties of soil, but there are other related objectives or sub-objectives, that if we compact a soil, the detrimental or undesirable settlement can be reduced, soil strength will increase, which will also increase the slope stability. Increase in the bearing capacity of pavement subgrades will also occur, so this will also increase the bearing capacity of the soil. Hydraulic conductivity can be decreased when we compact the soil, and undesirable volumetric changes, for example, which are occurring due to the frost action, swelling and shrinkage, these volumetric changes can also be controlled and can be reduced for various practical problems. Now, compaction of soils is achieved by reducing the volume of voids, as you can see in a non-compacted particle arrangement or loose soil. You can clearly see the voids volume is greater, and we can see the large pores here, but when we compact this soil, we will be having small pores, as we can see in this figure, much compact or denser configuration. It is assumed that the compaction process does not decrease the volume of solids or soil grains, so you can clearly see that those particles are not being crushed, or in other words, we can say that there are no volumetric changes which are occurring in the solid particles. Now, what is the difference between the compaction and consolidation? Compaction is a rapid process of reduction of volume by mechanical means, whereas consolidation is a gradual process of reduction of volume under the sustained static loading. Compaction is an artificial process which is done to improve its properties before it is put to end use, whereas consolidation is a process which occurs in nature, subjected to static loads caused by the weight of the supporting structure, or even due to the weight of itself, weight of those particles. In compaction, the volume of soil decreases because of the expulsion of air from the voids at the unaltered water content, whereas in consolidation causes a reduction in volume of a saturated soil due to the squeezing out of water from the soil. So this is the major difference, that in compaction air is removed, while in consolidation water is being squeezed out from the particular soil. Let us take a real soil, and this is the idealized three-phase diagram. And this three-phase diagram is shown for a loose soil. And now, after compacting this soil, this is the real soil. And this is the idealized three-phase diagram for a compacted soil. And you can clearly see that the volume of solids here and here remains same. Volume of water almost same, and the reduction in the volume of air can be clearly seen in the case of compaction. However, in consolidation, if we take the real soil and the three-phase diagram of a two-phase diagram here, because the soil is completely saturated, which means that there are no air voids present in it, then this will be the volume of water and the solids volume remains the same. And in consolidation, which is a time dependent phenomena, the water is being squeezed out from the soil. Now, discussing the fundamentals of compaction. The degree of compaction of a soil is measured in terms of its dry unit weight. During compaction, water is added to the soil. It acts as a softening agent on the particles. The soil particles slip over each other and move into a densely packed position. So initially, if it was difficult to compact this soil, or even this one, and if you add water into it, so it will lubricate and soften during the compaction process. Or in other words, we can say the fractional characteristics of this particular soil will decrease if water is present in between these soil particles. And if we place rammer on it, or if we roll it, then this will be easily compacted into denser configuration. Now, the dry unit weight during compaction first increases as the moisture content increases. For example, if we want to draw the moist unit weight and the moisture content, so moisture content on the x-axis and moist unit weight on the y-axis, initially if we start with the dry condition and we are adding water, what will happen that it will initially increase and it will reach to a point by changing the water content, and then after a certain amount of water, further increase in the water content will decrease the unit weight or the moist unit weight of that particular soil. When the moisture content is gradually increased and the same compactive effort is used for the compaction, the unit weight of the soil solids in a unit volume gradually increases. Again, we are discussing the previous figure, that if we plot the moisture content and the moist unit weight. At start, at 0 water content, gamma 1 is equal to gamma d, that would be the dry unit weight. But as we are adding water, for example W1, it will increase the unit weight, that would be gamma 2. And again we will reach to a certain point, or the maximum point, for the moist unit weight. We can call that as gamma 3. So gamma d will be equal to gamma d plus any change in the dry unit weight, or in other words we can say beyond a certain water content, W is equal to W2, any increase in the moisture content tends to reduce the dry unit weight. We are talking about the right side of the optimum moisture content, which I am going to explain in coming slides. And this is the gamma d, or this is plotted as moist unit weight, so we can call that as gamma, the maximum moist unit weight. Now why it's happening in such a way that initially the unit weight is increasing, but after reaching to optimum moisture content there is reduction in the unit weight of that particular soil, because the water takes up the spaces that would have been occupied by the solid particles. So initially the solid particles were taking those spaces in that particular soil, but now when you are adding more water, the water is taking the space which was taken by those solid particles, and that will definitely decrease the unit weight of that particular soil. Now the compaction curve, which can be drawn by standard Proctor test or modified Proctor test, which will be discussed in the part 2 of the soil compaction lecture. The compaction curve shows a relationship between a soil water content and the dry unit weight. Now we need to find out the maximum dry unit weight at the optimum moisture content. We need to find out the maximum dry unit weight, gamma d max, and this is the optimum moisture content at which, or the water content at which, the maximum dry unit weight is obtained. And this one point here, this shows one test, standard Proctor test or modified Proctor test. It is observed that the dry density increases with the increase in the water content till the maximum density is attained. With further increase in the water content, the dry density decreases, as discussed in our previous slide. Now, what is optimum moisture content? The water content corresponding to the maximum dry unit weight is called the optimum moisture content. We need to note down that the maximum dry unit weight is only a maximum for a specific compactive effort. For example, if we are using standard Proctor test, the gamma d and optimum moisture content will be different, and if we are using the modified Proctor test, just for the time being you can take as a different compactive effort and a method of compaction. For example, if we are dealing with the different types of rollers, such as works on the kneading action or the dynamic action or the static action, that will also change the unit weight and the required optimum moisture content to compact that soil. Each compactive effort for a given soil has its own optimum moisture content, and as the compactive effort is increased, the maximum dry density generally increases and the optimum moisture content increases. As you can see here, that if we take this compaction curve obtained from the standard Proctor test, now we are going to perform the modified Proctor test, in which the weight of rammer and the height of fall, number of layers are changed. So you can clearly see that the gamma D, or the dry unit weight, the maximum dry unit weight values are different, and even the optimum moisture content values are also different. Optimum moisture content values are decreasing, while you can clearly see that the maximum dry unit weight is increased if we are using higher, greater compactive effort. Smaller compactive effort. Now there is a zero air voids curve or a saturation line. The curve represents the fully saturated condition. S is equal to, the degree of saturation is 100%. It cannot be reached by the compaction. So this is the equation to draw the zero air voids line, where from the phase relationships we know that if we take that S is equal to 100%, so E will be equal to WGS, and if we put it in this equation, and for the various water content, we can draw this line, which is zero air voids line. Please note down that the zero air voids line must lie towards the right side of this compaction curve, and this compaction curve cannot reach to the zero air voids line. There is another line which can be drawn from the maximum, the dry maximum unit weight, or the peaks of the compaction curve. A line drawn from the peak points of several compaction curves at different compactive efforts for the same soil. So for different compactive efforts and for the same soil will be almost parallel to the zero air voids curve, and that line is known as line of optimums, and this is approximately parallel to the line of optimum. The zero air voids and the line of optimums are approximately parallel. Now, what are the factors affecting the compaction? If we change the water content, what will happen? If we change the degree of saturation, what will happen to the compaction, whether it will increase or it will decrease? If we change the type of soil, amount of compaction, and method of compaction. Let's start with the water content first. As we discussed in our previous slides, at low water content, the soil is initially stiff and offers more resistance to compaction. So it's difficult to compact a dry soil. As the water content is increased, the soil particles get lubricated and it's easily compacted into a denser configuration. The soil mass becomes more workable and the particles have closer packing or denser configuration. Now the dry density of the soil increases with the increase in the water content till the optimum water content. As we discussed in the optimum the compaction curve, Now the degree of saturation, we can draw the zero air voids curve, and the theoretical dry unit weight decreases as the degree of saturation increases, and that you can link to the lubrication there. The mass of air is negligible, so as the air replaces water in the void space, the volume of soil remains constant but its mass decreases, thus the dry unit weight. But here we need to reach to the optimum moisture content, but if there is too much water present, then the mass of air is negligible, so as the air replaces water in the void space, the volume of soil remains constant but its mass decreases, thus the dry unit weight will decrease. And you can clearly see that as the degree of saturation is reduced, the unit weight has also been reduced. In general, if you are talking about the type of soil, the coarse grained soils can be compacted to a higher dry density than the fine grained soils. With the addition of small quantity of fines to a coarse grained soil, the soil attains a much higher dry density for the same compactive effort. Now, if you are adding a small quantity of fine particles, so they may occupy the void spaces and they can increase the rate of the solids in this particular volume. But if you further increase, I would say more than 7% or 10% of fine content, what's going to happen? Those fine particles will displace those bigger solid particles, which can reduce the weight in this particular soil. So I would say that 5 to 7% fines will increase the unit weight, but more than 7%, if fines content is more than 7%, this will decrease the unit weight of the soil. However, if the quantity of fines is increased to a value more than that required to fill the voids of the coarse grained soils, the maximum dry density decreases. A well-graded sand attains a much higher dry density than a poorly graded soil, and that is also shown in the moisture content versus dry unit weight for the poorly graded, highly plastic, silty clay and sandy silt are different types of soil. Now we discussed about the amount of compaction. I would call that as compaction effort. And if you plot the moisture content and dry density on the y-axis, dry unit weight, and moisture content on the x-axis, if we are increasing the compaction effort for 20 blows, for 25 blows, for 30 blows, and you can see for the compaction curve for the 50 blows, we can clearly see that the dry unit weight is increasing and the optimum moisture content is decreasing. Now at a water content less than the optimum, the effect of increased compaction is more predominant, that is, the dry density increased. At a water content more than the optimum, so it's on the, I would say this is the line of optimum, the effect is greater if we are on the dry side of the line of optimum or on the left side of the line of optimum, and the effect of compaction effort is not that much great when we are on the right side of the line of optimum or on the wet side of the compaction curve. The effect of increased compaction is not that significant. As the compaction effort is increased, the maximum dry unit weight of the compaction is also increased. As the compaction effort is increased, the optimum moisture content is decreased to some extent. So initially, if 16.5% of water content was required to reach to the maximum dry unit weight, now by increasing the compaction effort, it will be required 14% of optimum moisture content is required to reach to the maximum dry unit weight. Now let us discuss the method of soil compaction, that whether if we change the method of soil compaction, that's going to change the maximum dry unit weight or the optimum moisture content conditions or not. Now the dry density is achieved depends not only upon the amount of compactive effort but also on the method of compaction. For the same amount of compactive effort, the dry density will depend upon whether the method of compaction utilizes the kneading action, it's mixing or squeezing the soil, the dynamic action, applying a dynamic load or applying a static load on that particular soil. There are various types of equipments used to compact the soil in the field, which will be discussed in part 2 of the lecture, but briefly explaining the method of compaction here, an example is given that in Harvard miniature compaction test, the soil is compacted by the kneading action, and therefore the compaction curve obtained is different from that obtained from the other conventional tests such as standard Proctor test or modified Proctor test, in which the equal compactive effort is applied. Now, different methods of compaction curve give their own compaction curves. Consequently, the lines of optimums are also different. Hence, the maximum dry unit weight and optimum moisture content will be different if you are using a sheep foot roller or if we are using dynamic action by rapid impact compactor, like the impact or force is applied to dynamically compact this particular soil. And here, using the sheep foot roller, the kneading action or the lugs or those feet are used to squeeze and mix this cohesive soil, and usually vibratory or dynamic loading is preferred in the granular soil to remove the air voids present in these types of soil. So thank you very much. That's all from the introductory lecture of the compaction or the part 1 lecture. See you in the part 2 of the soil compaction, where we are going to discuss about the standard Proctor test, modified Proctor test, different types of equipments which are used in the field, and also we are going to discuss about the equipments in the field and the tests which are used to find out the dry density in the field. So I hope you're enjoying our videos. Please kindly like, share and subscribe to our YouTube channel. Assalamu alaikum and Allah Hafiz. Take care.